Good morning, everybody. I'm Alex. This is Alex, and that's also Alex. I'm Alex Cook, and I split time at the CSD and on the Island School faculty.
Hello, everybody. My name is Alex Perkins. I'm an environmental engineer and research advisor at CSD, working on waste to energy systems. Our team is very excited to tell you about another way to repurpose waste at the Island School and beyond.
All right, so we're the Fall 2016 Repurposing Waste team. I'm Soren Barclay.
I'm Chuchi Munson.
I'm Gabriel Garcia. I'm Alex Ackerman.
I'm Amaya Smokete. I'm Morgan Krasovich.
And this is plastic pyrolysis and waste to energy potential at the Island School. So I'm just going to tell you a little bit about our project and why it's important. This is the Harrow Road landfill in Nassau. Every year, in landfills like this, plastic is burned to reduce its volume. I don't need to give you a fancy statistic or a memorized fact to tell you why this is bad. Just looking at this picture should tell you why this is bad. Just looking at this picture should make you care about finding an eco-friendly alternative to how we deal with plastic. The fact that 2 of our 8 research projects here are plastic-based should tell you why this is a problem. The fact that you can take a 2-minute walk over to CSD and see 4.5 tons of trash should tell you why we need to find a solution. But more importantly, the fact that when this landfill burned, kids had to stay home from school because if they went outside, it meant risking their safety and inhaling carcinogenic fumes, tells you that we need to find a solution. So one of our main goals here at the Island School is to be a zero waste campus. This means that all of the waste that is produced here is managed here. This is especially difficult living on an island as we have to import a lot of goods and this produces a lot of waste. But through plastic pyrolysis, we will be able to pyrolyze all of our plastic waste and turn it into usable fuel, bringing us one step closer to becoming a zero waste campus.
To reach this goal, we need to understand where plastic comes from and how we get rid of it. Crude oil is extracted out of the ground and refined down into these different plastics that, unfortunately, most of the time are single-use plastics. For example, you buy your steak from the store, you take off the plastic wrap, and you throw it away. There it goes. What can happen to that plastic is now one of 3 different options. When it's in the trash, one of the options is going to a landfill. When it's in your trash, how does it get to the landfill? It needs some sort of transportation, and that transportation puts emissions into the air, contributing to its carbon footprint. But not only with the transportation, once it reaches the landfill, especially here in the Bahamas, like Soren said, they're set on fire to reduce the volume, which creates that horrible black cloud of smoke filled with toxic emissions, dioxins, and unburnt plastic particles into the air that risks people's safety from inhaling it. Overall, this is not where we want to be sending our plastic waste. The other option is through recycling. And recycling is a worldwide accepted way to deal with our plastic, to give it a second use. But plastic cannot be recycled indefinitely. For example, these shirts, they're made out of recycled plastic. That's great, we wear them, we look stylish, it gave it a second use. But what happens when this shirt gets a hole in it, or when we can't use it anymore? We have to throw it away. It goes to a landfill, it creates this huge black smoke. It's not gonna deal with the plastic forever. And especially here on Eleuthera, we don't have the means to recycle plastic, so we have to ship all of our plastic waste off the island. That takes money away from us and also puts emissions into the air through the shipping process, which lowers the overall value of the plastic and makes the process for us just not worth our time. So that's why we've been looking for an environmentally friendly and financially feasible way to deal with our plastic at the Island School, and that is through pyrolyzing it into a usable fuel.
So these are our goals and questions into this project. Is pyrolysis feasible? Is pyrolysis even possible? And if it is possible, what is going to be feasible from the Island School? Where is the product of plastic pyrolysis? Can we create usable oil? How much plastic waste do the island school produce? Is it going to be good for us to have a pyrolysis machine around in campus? And what is the waste to energy potential at the island school? If we get translate all our plastic into useful oil, can we use it into our vans and machines?
So pyrolysis is thermal decomposition at a high temperature, low oxygen environment. Due to the lack of oxygen in this process, pyrolysis is not the same as burning. In our case, pyrolysis takes the long hydrocarbon chains of plastic and cracks them into smaller, much shorter chains in the form of liquids and gas. The pyrolysis process begins in our airtight reaction vessel, where plastic is heated at a temperature of at least 500 degrees Celsius. The high heat and lack of oxygen breaks the bonds of the hydrocarbon chains, converting the plastic into a gaseous state, which is then fed through copper piping and condensed into a liquid in a glass of water at the end of the pipe. All non-condensable gases are released through bubbles in the collection vessel, and all condensed product is collected on the surface of the water in the form of fuel. This entire process takes about 45 minutes to complete. This here is an image of our reaction vessel made up of repurposed materials from around campus. 100-gram samples of plastic are used in each experiment. Once the process is complete, we separate the water from the oil and measure the collected product. We also test the flammability of the product to determine whether or not it is fuel.
So as stated before, we take 100-gram samples of each plastic that we pyrolyze, and some of the plastics that we use, as you can see here, are yogurt containers, egg cartons, bleach bottles, packaging, and refrigerator shelving. Afterwards, we cut up the plastic and we put it into our reaction vessel, as you saw earlier on in the slideshow, and we put it into an oven, as you can see here. Afterward, the plastic is turned into a gaseous state and condenses down into the oil as played in this video. Once that is done, the water is removed from the oil and it's collected into our repurposed glass vessels, and these are one of the vessels here. And all different type of plastics give you different consistency of oil depending on which one it is. These are our results from our studies. Table 1 here shows us the average calorific value of both diesel and waste plastic number 2. And this shows us that when waste plastic number 2 is pyrolyzed, it has the potential of replacing diesel because of its similar potential energy. And it also shows us that waste plastic number 2 is only 8% less efficient than diesel. Table 2 here shows us the product volume of each plastic that we have, which are plastics 1, 2, 4, 5, and 6. We currently do not have any results gathered for plastic number 1 due to the potential oil clogging the piping. This graph shows us the average fuel production for each plastic. The standard deviation bars that you see on the top shows us the variation of data that we collected for each plastic. Plastics 5 and 6 appear to have higher product collection, and this is due to us fixing the pyrolyzer later on in the experiment, in the study, and pyrolyzing these plastics later on, as 2 and 4 have lower production collection due to us pyrolyzing these plastics earlier on and noticing the fact that some of the potential oil escaped.
This is a graph showing the weights and percentages of each type of plastic that we collect at the island school. As you can see, we have higher amounts of number 1 and number 2 plastic and lower amounts of number 4 and number 6 plastic. So what can we do with our product? Well, one option we have is to put it in our vans. The average island school van drives around 19,000 miles a year. In that one van, we could put in our fuel and it could drive over 11,000 miles. That would offset 60% of what that van would need for the year. Another way we could use our fuel is in energy. As you can see here, we have our load, our average consumption on a November day. Over here, we have our wind and solar that we actually produced on that day. Above that is what we could possibly do with pyrolysis. It would be a 25% increase to our renewable energy production. In the future, we plan to analyze our fuel and oil that we produced to assess its makeup and the usability. We also hope to look at the financial feasibility at the island school and then develop a full-scale pyrolyzer on campus to deal with all of our plastic waste. This would get us one step closer to being a zero-waste campus, and we would be a model for other communities facing similar problems to us. And it would also change plastic's inevitable path to a landfill. This is our literature cited. We would like to thank all of the CSD staff for helping us with our project, especially Mark, Mike, and Sarah, Robert Klein from Clean Sea Fuels, Dr. Robert C. Brown from Iowa State University. Are there any questions? Yes.
So I know this probably will come out when you do the financial study, but have you looked into how much energy you actually have to put into your furnace or stove actually, and how much fuel you get out? So is there a net positive there?
The question is, how much energy do we need to put into the initial reaction to start it?
What are you using? How much energy are you using to create that fuel? So
Yeah.
it's balanced.
Okay, the question is, how much energy are we putting into the process? Well, the answer is that the energy we put in is 40 times less than the energy we get out in that fuel. So there is a positive net. Yes.
The water that comes out of the pyrolysis process is a byproduct, reusable, and what do you do with it?
The water that, the question was, is the water that comes out a byproduct and what do we do with it? The water that's in the collection vessel, we actually place there as a condenser so that the oil would become a liquid. So it's not actually a byproduct of the pyrolysis itself.
So is the pyrolysis producing both oil and gas? Are you not capturing the gas it is producing?
Is the pyrolysis producing oil and gas, and what do we do with it?
The answer is yes, it's producing oil and gas. Like I said, the non-condensable gases are released through bubbles in the collection vessel, but we haven't been able to do this with our design, but what we plan to do in the future is capture those gases and feed those back into our heat source and light those on fire to create a closed loop system. Yes.
Are any toxins released through this? If you have burning that releases toxic fumes, is any toxins released in the pyrolysis method?
So the question was, are any toxins released during pyrolysis? Well, there are only non-condensable gases released because this is not burning. It's simply just heating up at a high temperature without oxygen, because burning requires the presence of oxygen. So we're simply taking hydrocarbons and just breaking them into smaller hydrocarbons, so we don't really end up with any toxins at the end. But like I said, we're trying to capture those released gases and use them as a heat source. Sure. The question was, can this be done on a large scale?
There are people doing it out there on a larger scale, like Robert from Clean Sea Fuels, so we've been working with them with our process. Yeah. Yes.
Do you know what the carbon footprint of burning the fuel you're producing is versus a more conventional or normal fossil fuel? How much carbon releases?
The question is how much carbon is released compared to other burning fossil fuels.
Wait, could you repeat the question one more time?
Yeah, so how much carbon is released when the fuel you're generating is burned in comparison to burning gas or oil?
It wasn't the focus of our study, but from what we've read in other readings, there was actually showings that it produced less emissions compared to other fuels.
So you guys gave a really great presentation on how I cool fats, but how do you know this actually works?
Glad you asked. The question is, does it actually work? And if you'd direct your attention to the back.
So this is not Snapple. This is what we call PB25, or 25% pyrolyzed plastic fuel, 75% biodiesel. Ready?
No, it's not gonna blow up. Want to give it a tug? Yeah. Yeah. You got it? Yep. Set? Yep.